Okay, I've been working on something to do with create aerodynamics / sables aerodynamic calculations. They were not very realistic, but they were quite fun and cartoonish. But I really wanted to see what it would be like with some real aerodynamics, at least as I understand how to do real aerodynamics from my aviation experience. Okay, so I'll basically go through what I've done very quickly. I'll try to be quick. So I have polar data for two different aerofoils, a cambered aerofoil and a symmetric aerofoil. So cambered aerofoil, we got for every single conceivable angle of attack, we have coefficient of lift, coefficient of drag, and coefficient of mass. And I calculate that using Q-Blade. It does basically, it's a plate solver for foils, uses X-foil as a backend to do that, but then past the still point, it uses flat plate aerodynamics, because what happens is when you go past the still point, the plate solver can't solve it accurately anymore, but in the aerofoil, the wing ends up behaving more like a flat plate. So these are coefficient of lift, coefficient of drag, and angle of, and coefficient of moment. Moment is just basically the rotational force caused by the aerodynamic, this center of pressure moving, basically. Okay. It's pretty nice having that data. It will make stills way more realistic, but you gotta actually use it. So how do I use it? I have created this code here. Is just stores it, the point, just stores references to these aerofoils, and then this is the function that actually loads it, and you store the data in basically a tree map. And the reason I use a tree map is because you can have any arbitrary angle of attack that needs to come in, and you get a template between them, and tree maps are ordered in the way they're stored. So it makes sense to use a tree map. Okay, then most of the heavy lifting in my changes is to the block sublevel lift provider. But I do add some extra things to this function call, like I get all of the lift providers passed in, I get the hash map passed in, because I need it to figure out certain properties about a wing. So this rejects any block that isn't any wing block that isn't the leading edge. So right now it's hard code. Oh god. Okay, I accidentally delete stuff from my mouse all the time. Right now it is hard coded to be the north direction. I will change that eventually when I come up with a way to do it, but right now you need to build your aircraft facing north if you were to use this code. So basically, okay, we're looking, if there's a block in front of it, so in the north direction, then it's not the leading edge. Well, a wing block specifically. Okay, then we count back to get the chord. So we count the blocks backwards to get the chord. So we're just looking south, basically. If there's a wing block, go back more, wing block, go back more. Okay, got the chord length. Okay, so now I know the chord length. Okay, then I can do some calculations. So instead of what they do, which is on every single block, it's just the center of the block that the forces are applied, the lift position is now the aerodynamic center, which is 25% of the chord length, which matches what my simulation in Q-foil did with these two airfoil profiles. Okay, it's pretty much the same. Okay, chord normal. Okay, so I calculate the chord normal, so that's just the forward direction. Pretty standard, using the span normal and wing normal. Wait, no, I calculate the span normal. Sorry, storing this in span normal, using the chord normal and wing normal. Chord normal is just north for now. Okay, because I need the span normal for certain calculations. This, I don't know if it works yet, but this is to do with contraptions, having lifting surfaces on contraptions. This is mostly the same as their code. This calculates the velocity at point. In this case, originally it was the velocity of the wing, but now it's the velocity at the aero center. Okay, I calculate the angle of attack. Oh god, I delete stuff from my mouse again. I don't know how I keep doing that. Okay, calculate the angle of attack. by using the forward velocity and up velocity component of the lift velocity center. But lift velo is just the velocity at this center of lift, which is 25% of the globe. Okay. Then basic math. So after we have the vertical and upwards component is a tan 2 and mass degrees d to get an angle in degrees from those two vectors. Okay. Let's see. Then right now, if the lift scalar is greater than 0, it is a Camber aerofoil. If it is not, it's a symmetrical aerofoil. Not the best way to do it, but it's just integrating with their code. I know that Aerodynamics as the symmetrical aerofoil, its lift scalar is set to 0, basically. It returns 0 for that function. Whereas the wing, well, not the wing, the sail returns like 4 point something. Because that was originally their coefficient of lift that they were using. It was fixed. Okay, and we use my function to get the actual coefficients, depending on the angle of attack. Okay, if the velocity at a point is greater than a very small number, 1 times 10 to the power of negative 12, very small. Okay, we calculate the string velocity, so that's not the velocity point, that's just the global velocity in reference to local space. Okay, and then after we have that local space, I can calculate the lift normal using the string velocity, because lift should be perpendicular to the string velocity. And then on the other axis, so not in this case because I've hardcoded it's not, on the other axis it should be perpendicular to them, but the actual forward-back axis should be perpendicular to the string velocity. Okay, then dynamic pressure, pretty simple, half times pressure times the velocity at the point of aerodynamic center squared. This is good because it wasn't squared originally, which made it very hard to build certain size aircraft with like lots of weight and stuff. Okay, drag force, pretty simple. We calculate induced drag using the we calculate induced drag, which is the lift coefficient squared divided by pi times it's a constant that determines the efficiency basically. It's an efficiency constant times the aspect ratio. Okay, and then we calculate the magnitude of drag, which is dynamic pressure times chord length. Reason it's just times chord length is because the slices I'm calculating if each slice is 1 block wide and times 1 is itself, so this is actually the surface area of the slice. Okay, times by the drag coefficient plus the induced drag coefficient. Okay, so yeah, having induced drag is pretty good because it means induced drag is created by vortices from air rolling from the bottom surface to the top surface. And I calculate that reasonably well now. High aspect ratio wings are more efficient. That's why aspect ratio is factored into that. I actually hijacked the flood fill in the group code, which I now make the group code run all the time to get that aspect ratio. Oh, but for whatever reason, if a group doesn't exist, I just assume the aspect ratio is 5. However, I'm pretty sure because I made it run all the time now, the group code, it should always be there. Okay. Okay, we just negate the lift velocity, normalize it to get a vector that is opposing the velocity at the aerodynamic center point. Okay, and then we just multiply that, the drag magnitude by that, and then add that to the aerodynamic forces. Easy. Okay, this is the group stuff here is it's predominantly meant for the blueprint system. I like to display the forces in the blueprint, so I do fill that information in. Okay, lift force, dynamic pressure, times chord length, times lift coefficient. Pretty simple, then multiply that by the lift normal that I calculated earlier, times, add that to the aero force. Okay, moment torque. So this is the moment using the moment coefficient. And this calculates basically the effective torque that would happen because of the center of pressure moving away from the aerodynamic center. So you might have rolling torque. It's good to have it because it makes aircraft actually more stable, and it is more realistic to have it. Okay, this is completely unnecessary. Aero force multiplied by the time step, that just converts the newtons into the impulse, and then we offset that by, then we offset the force because the force is calculated at the center of mass. We offset it by the lift position, and basically apply the force. Then I apply the angular impulse and the moment torque. Okay, that's pretty simple. That's pretty much most of the changes. So it's much more realistic now. You can see how it behaves here. Let's see. Here we go. This is just a test truck plane that I have created. Okay, so if I drop it, there we go. It's gliding. So it is in fact working. You can see that if I throw it a little bit off center, so I'll just give it some forward velocity, and this is how it pretty much aggressively comes back to straight. That's because there's actually lift forces on the symmetrical force now that oppose, they basically stabilize it. Because traveling like this, there is now a lift, there's an angle of attack that's producing a lift force that wants to rotate this wing back to center, as you can see. So I can throw it more aggressively. Right now things are pretty floaty because I haven't tuned anything yet, and masses are pretty light in crate aeronautics, and this aircraft is predominantly made out of wool. So it's pretty light and has a lot of drag, but a lot of lift as well, because it's got a lot of wings for its plane. So there we go. That goes back to center pretty nice. I can show you stalling. So let's lock it. Let's make it stall. Okay, I can do that by just adding some blocks to the back of it that will make it pitch up. Okay, so it's pitching up and it is stalling. Okay, let's give it some forward velocity. Okay, so it's got some forward velocity, it's pitching, and it's stalling. And now it's flying backwards. Okay. And now it starts slipping. It seems mostly correct. Things might be better if I had an engine. Hold on a sec. There are still a few issues I have to solve. For some reason, when you get things moving quite fast, things can definitely go wrong. And I believe there is some situations where there's a feedback loop that I haven't exactly figured out how to cause yet, but every now and then I do cause a feedback loop. Okay, so, okay, it is flying. Actually, that's working pretty well. Okay, let's shift the center of mass back a bit to pitch up. Okay, here we go, climbing. Okay, fly right, fly left. Okay. Yeah, this should be much more realistic. It still needs some refinement. I still need to tune it, and I definitely need to figure out the issues that can send stuff to hyperspace and then losing your vehicle. That can happen in the normal game too, but I think it is more likely than I could. I've had it happen a few times. That's why I created a bunch of backup builds so I didn't have to build the plane each time. And I need to come up with a solution so you don't have to build the plane facing north, because that's not very nice. But yeah, right now, if you were to use this code, you have to build a plane facing north. But yeah, I'm not going to release it yet. I'm going to fine tune it, and possibly instead of just editing Sable itself, making a mod that uses mixins to mix in my code. However, I did change quite a few files, so it can be a bit blah using mixins. But I'll figure it out. But yeah, this feels very nice. Even though I haven't got it tuned yet. Like, this is the result I got after I got it working. And I'm like, huh, this actually feels pretty nice. Okay, we're stalling. And yeah, that's a stall. Well, a power stall. Yeah, let's increase the thrust. Let's add another engine. Boom. Oh god. Oh fuck, they're facing the wrong way. No, whatever. Bam. Okay. More thrust. Pitch up. Come on. That's nice. There's a lot more drag on this. If we go to the full center of mass, it's pretty close to the center of lift. Okay, drag. Like 700, 600. Yeah, 5,000 on the wing, but the wing is huge, so that makes sense. And actually, increasing the aspect ratio should improve the efficiency. So it should flow a little faster now, technically. And I'm just going to get more turning torque now. Oh god. It's stuck in the roll. Jesus Christ. Yeah, still needs some tuning, but it's very nice. I'm definitely getting a lot of lift now though. Yeah, drag's definitely changed. I'm pretty sure. By increasing the aspect ratio. Leave on those, wait. That's better. Now, there we go. Okay, rotate, come on. High aspect ratio wings have more inertia, so they don't like to rotate as much. The center of mass changes. So hand gliders with high aspect ratios actually warp the wing in order to help steer with weight shift changes. Okay. This is pretty nice. Okay, let's try it. Give it into a dive to see how fast I can get it going. Okay, we are speeding up now. But there's still a lot of drag. We still have juice drag too. Oh boy. And we're getting a lot of, because of that speed, we're getting a lot of moment torque as well. We're going down there once the fish. It's very nice. Tip stools are interesting. You can definitely get tip stools. Okay. Oh god, we're gonna stall. Yeah, we're tip stalling a bit. So it's starting to roll to the right now pretty rapidly as we're tip stalling. And then it will recover speed. And as it recovers speed, it will unstall. Okay, pitch up, pitch up. Pitch up! Ah! And fuck. I hit it. Okay, so yeah, that's that. That was actually working very well. Alright, that's what I've got so far.